This is the cytoskeleton microtubule anatomy. Here are a couple abbreviations that you're going to see. MT for microtubule, and for alpha tubulin, I'll use any of these abbreviations, likewise for beta tubulin. I also want to remind you to think of the analogy of each microtubule as a single straw, like a drinking straw, and that they are hollow, as you can see here, and they're reasonably rigid and kind of hard to work with. One thing you should notice is that unlike drinking straws, which have that little bendy section, microtubules do not have a bendy section. They also tend to cluster together through some organizational methods, and so like you see here, there are many different straws that would be analogous to many different microtubules that are all clustered together. I also want to remind you about this sheet, which we went through in class, and these take-home messages are really useful to kind of get your head in the game and pay attention to some of these big themes as you look at today's topic, which is microtubules. As a reminder, we're talking about microtubules today. There are two other types of the cytoskeleton, and microtubules, their big role is to move items within the cell and position organelles. The big thing here to notice is this is within the cell, and I use the analogy of a zip line, like here. On the other hand, when the entire cell moves, that's due to actin. This is figure 17-10, and basically we're looking at microtubule anatomy. First off, the smallest building block for the microtubule are the tubulin proteins. There are two different types of tubulin protein, alpha tubulin and beta tubulin. They are each globular proteins, and they're pretty similar in terms of structure. However, notice in the book that they color code these with two different shades of green, alpha with the light green and beta with the dark green. It's not so important that you know which one is which, but do notice that that difference is indicating a polarity. The subunit of the microtubule is the heterodimer, and the heterodimer is made up of one alpha tubulin subunit as well as one beta tubulin subunit. And so we see that over here, and they are held to each other through non-covalent binding. This is pretty strong non-covalent binding. Heterodimers will stack together to make a protofilament, which you can see along here. This is a linear chain of alternating alpha tubulin and beta tubulin subunits. Naturally, they're held together through heterodimers, and so those will sort together kind of as like little unit. Each protofilament is polarized, meaning that it has two different sides which are distinguishable from each other, and they are called the plus end and the minus end. Notice that this is not due to electrical charge, it's just named that way. It has to do with the growth experiment that was done some time ago, an in vitro experiment in which the polymerization was seen to be more rapid at the plus end. And as you can see, the plus end corresponds to beta tubulin and the minus end corresponds to alpha tubulin. So we see that over here. So we would say that overall for this whole protofilament that there's this plus end and the minus end. 13 protofilaments together will make up one microtubule. And so basically, if you check out over here, we've got the 13 protofilaments. So this long way, 13 of those all stack next to each other. They're all held together through non-covalent interactions. And basically, that's one microtubule. If you were to take this whole long rod and turn it on its end towards you, you'd see this. Notice that here we see all the beta subunits pointing towards us, that darker green. And then there's this hollow area in the middle. They call that a lumen, but really you just need to know that that's hollow. Note that the polarity of the microtubule is incredibly important, not just for the heterodimer, but also for the overall microtubule. And there's two major reasons for that. First off, polymerization takes place differently depending on which side of the microtubule we're talking about. And then secondly, for the functionality of microtubules after they're assembled, this is going to set them up for what they can do. And so one of the things that it's critical for is for that zip line of intracellular transport, for example, for moving vesicles across the cell. The zip line motors only work in one direction, and so that has to do with the plus end versus the minus end of the microtubule. Finally, if you want to see a little bit about microtubule polymerization, check out The Inner Life of the Cell. I like this full version that's narrated, and there's just a real tiny clip, 314 to 324, and that shows the assembly of the heterodimers of the microtubules to make this hollow rod.